I will just introduce Mark Anderson. He is an engineering consultant at Staties Incorporated. And prior to joining Staties, he spearheaded an award-winning quality improvement program for an international manufacturing that generated millions of dollars in profit. And he has so much experience in process development, quality assurance, marketing, purchasing, and just general management. He's also the lead author of 3 textbooks. It's our trilogy, DOE Simplified, RSM Simplified, and Formulation Simplified, that are used both for researchers to study and for academics to learn, really the practical hands-on ideas of design of experiments. He's also published hundreds of articles on design of experiments. He is a chemical engineer by first degree and has an MBA to top that off, and he is a certified quality engineer. So with that, I'm going to turn this over to Mark Anderson.
Thanks a lot, Sherry. Am I coming through okay on audio?
Yes, you are. You're good to go.
Perfect. Okay. So welcome everybody to this summit in 2023. It's a pleasure to start it off with something fun. I like the motto of the Boy Scouts. I've got 2 Boy Scouts that made it all the way through to the highest levels, and their motto was always keep it simple and make it fun. And this was important when I was a Webelos den leader in 5th grade with 13 kids. It was really important to keep it simple and make it fun. And I found that that translates very well to statistics, which can be very daunting and off-putting. And applying that same approach to the application of DOE to try to get it to be embraced as a tremendously effective multi-factor, multi-component approach. Now, this experiment combines process type factors with mixture components, and it's typically what you're going to run across in your kitchen when you're trying to work on your recipe and see if you can come up with a better way of mixing it up and baking it too. So I was very happy when Greg Hutto came forward with a student that was going to work on this as a project. So straight away, I have to give a lot of credit to Greg and his student, Jessica, for actually doing most of the work. And I was able to provide advice. And I want to report, what happened, because it's a very innovative type approach. So I'll go ahead then and start the slideshow. And so to begin with, I just want to make sure that everybody is with me by exercising in your control panel that little raise hand button, and press that button, and then we know that you're with us.
Mark, I'm not hearing you anymore.
Okay, there was a temporary little glitch there with the audio, but I'm back again. The wonders of working across the internet at a distance. So Sherry, I presume that you're hearing me again.
Yes, we are good. Thank you.
Perfect. Okay, so pressing ahead then, let's start talking about this chocolate chip cookie experiment. So keeping it simple, making it fun is the key, I think, in presenting. But as an attendee, of course, you're always asking, what's in it for me? And so I always like to lay that out at the beginning. It's something that I learned when I first started studying how to speak with Toastmasters Club. And they said, to begin with, if you don't convince the audience that this presentation has something for them, then you're really not going to make any progress. So here's some of the ideas that I have here for this presentation. First of all, it's going to illustrate, as Sherry said, a more complex type structure that's called a split plot. And the split plot is something that is very effective for dealing with hard to change or HTC factors, we call them, and then combining that with factors that are easy to change or components, we'll call those ETC. And it turns out in this case that if we consider the time and temperature in the oven as the hard to change and the mixture of the chocolate chip cookies as the easy to change, then this will be a very nice structure for us to make a practical experiment. I also am going to demonstrate a model called Kowalski Cornell Vining, or KCV, that minimizes the number of runs in these combined mixture process designs while retaining the ability to detect synergistic combinations of the component factor combinations. And this is really a big breakthrough that came about 10 years ago. And it's a very clever way of crossing the two models. The typical model for process is called a quadratic equation. It's a polynomial model. And the model that we use for mixture design is called a Chaffee. It's got a different structure to it to account for the fact that the ingredients add up to a fixed amount. And if you simply just brute force multiply them together, you end up with many, many terms that require individual runs to try to set. But the KCV model simply crosses the main component effects with the main effects of the process, and then the other terms are left alone. And I'll show you that as we go along, but what's really important is the end result of it is you have to do fewer cookies to bake to get that advantage of learning how the components interact with the factor settings. Then also kind of a little added PS to this whole thing is the idea of blocking, which is a very important tool for DOE to break up your design into more doable chunks. And in this case, the experimenter, Jessica, needed to do this over a weekend because she had a day job. She was going to night school for DOE class that Greg Hutto was teaching. She needed to get these experiments done on Saturday and Sunday. And so she blocked the design into two groups, Saturday versus Sunday, which made it easy for production and also for the people tasting the cookies not to get overwhelmed. So here's a picture of Greg. As you can see, he's a very jolly fellow, very well spoken. He's been a speaker for DOE Summit in the past, and I've had the pleasure to visit with him down on the Panhandle of Florida at Eglin Air Force Base, where he spent a lot of time working. And he's now doing teaching as an adjunct professor with the Northwest Florida campus of University of Arkansas. So Greg contacted me, I guess it was last spring, and he said he had a student, Jessica Keel, who wanted to do an experiment to modify cakey chocolate chip cookies, a recipe from the Martha Stewart test kitchen. And she thought it would be interesting to vary the relative amounts of butter, granulated and brown sugar, and vanilla, and then bake those at differing times and temperatures. Now, Greg has done, a lot of work with U.S. Air Force in a completely different arena than what I'm used to as a chemical engineer. So it's kind of like we've been operating in two different, worlds here using DOE for different applications. So why not get together and have a synergistic combination? And Greg was, not hesitant to contact me and saying, hey, here's what I have in mind. What do you think? So we kind of put our heads together, got together with Jessica, and we put together a study that involves the mixture for the recipe, and then the process factors of time and temperature. and put this into this split plot to deal with the hard to change, oven temperature type situation. Then we also applied this KCV modeling, which resulted in a much smaller design. So I was pretty excited about applying this. So we went ahead and started working on it. And so we dealt with this very tricky combination of mixture components and process factors. Now, of course, we want to randomize where we can, and where we can't, we start to group things in the split plot structure. And George Box was, very practical about this. I was lucky enough to attend training in Madison back in the mid-1990s. And he had a very practical focus of randomize as much as you can. What you can't randomize, break into a split plot with hard to change. And if push comes to shove, run the experiment however you possibly can, rather than not running the DOE, which I think is good advice. So what we ended up doing then was setting up a split plot, and let's get into a few details on this flavor of DOE. So the problem is that often in design experiments, some of the factors are more difficult or expensive to vary than others. And so it's not practical to run a randomized experiment. So the solution is to restrict the randomization. Then it becomes a lot more practical. So this design, really originated with the developments of Sir Ronald Fisher in the 1920s. So at the very beginning, he had this problem for doing agronomy experiments. And I imagine back then they would have had a biplane coming through, and it would have been applying some kind of fertilizer or herbicide to these crops. And the trouble is that it's going to be spraying over some area. So this is my little airplane here, very poorly drawn. What we've done is we've broken up this strip of land here into subplots. And as we go over the first one in a randomized fashion, the pilot switches over to herbicide B, and he's spraying across corn, potato, and squash, randomly divided into this whole plot. So there's 3 subplots here, and he's flying over and he's spraying, herbicide B across here. He's flying back over here. There's a buffer area in between for the overspray. And now he switches the tank over to herbicide A. Now notice that the subplots within this whole plot are still corn, squash, and potato, but it's in a different order. Obviously, if we had more types of crops, this would be more obvious that there's a randomization occurring within the subplot. So now he sprays herbicide A, and then he flies around over here, switches the tank to the last herbicide C, and sprays that. And notice again, we have a randomized order of these subplots. It's now potato, corn, and squash. So by doing it this way, we don't have to try to deal with, coming down each of these individual subplots and then randomly switching over from the herbicides, which would be completely impractical. So we've got a grouping going on into whole plots, which is the hard to change factor, the herbicide. And then we have subplots that are randomly applied within the whole plots. And those are the easy to change factors. Now this naturally arises, the split plot design structure, when you combine mixture and process variables. So the chocolate chip cookie example is exactly what I've been bringing up for some years now when I get to this stage of combining. And I always imagine, trying to make chocolate chip cookies, and a totally randomized plan would be to make one individual cookie according to whatever your randomized recipe sheet says. Take that one cookie and put one cookie on one tray and put it in the oven and bake it at whatever the settings are for the process factors at time and temperature. And it really would be silly to do it that way. I mean, obviously, the first thing that you would think about is making individual cookies and then at random, and then put them on a tray and then make the process factors hard to change, so that once you get a whole tray full of randomized cookies onto the tray, you put it in the oven and then you set it at whatever the time and temperature is. And, that's one batch. Then you go back and make another randomized tray and then go back to the oven with different times and temperatures. And you'll see this in the structure from Jessica. So that would be this side of the structure. On the other hand, we could flip this and we could mix up an entire batch of cookies at whatever the recipe calls for, and then bake one cookie at a time. And this fits into more of this structure. Now the triangles, if you're not aware of this, represent the mixtures. And this is what's called a ternary diagram. And you're going, to 100% of ingredient A at the top of the triangle, and you're going to 100% of ingredient B at the lower left corner, and 100% of C at the lower right corner. All right, and then in the left side, we've got triangles superimposed over the corner of the square. The square represents the process space. And, in this process space, we might have a factor, let's say A, that's going from low to high in this structure, and then B is going from low to high from the bottom to the top. Now we flip it over here on the right side, and we draw the triangle first, and then we put squares at each of the mixtures. And in this setup, we've got binary blends. So this would be an AB blend at 50-50. For example, and here we have an AC blend and then a BC blend at the bottom, so at the midpoints of these edges. Okay, and then again at the corners is 100% of A, B, and C. And we could actually put a point in the middle, which would be what's called the centroid, or 1/3, 1/3, 1/3. All right, but you can see what's going to happen here is that the combinations are going to start to explode because we're crossing the experimentation on the mixture with the experimentation on the process, and there's just a lot of variables that come into play here. So it begins to get kind of out of control. Okay, so which way should we go? The left side or the right side? Well, generally speaking, you're going on the left side because most people don't have one of these little pink easy bake ovens handy in your bottom drawer. But we have one of these easy bake ovens that we use when we were raising our 5 kids to play around. And there's a little light bulb in here that heats up, one individual cookie, or maybe you could put 2 in, but generally just one. And so this would be the case where we would be going to this side here. This would be the easy bake oven approach if you wanted to go that route, but it would be, fairly intensive and not very well controlled experiment. So then the obvious thing was that it would be much better to make up a tray of cookies made by varying recipes and then bake them grouped on the trays. Now, the last time I tried this, I didn't do very well trying to get the feedback from the group. But let me just try it again. And if Sherry's listening, maybe she can see, because I'm not sure I'm going to be able to see it. But if you could press that raise hand button and let me know if you're with me so far. And then Sherry, maybe you can report back to me because I'm not getting it on the control panel.
Hi. Yes, there are a whole bunch of people who have raised their hands.
Perfect. Okay, I appreciate that. Thanks, Sherry, and thanks everybody for listening and paying attention. It's been quite an interesting run since the pandemic came in March of 2020, and we flipped our classes over to Zoom and started working at a distance that was so abrupt. And I like it. It's great to be working out of my office here in Stillwater, Minnesota, and then in the winter I have a home down in Florida that I can go to and work out of the home in Florida, and open up the windows wide open. But not being able to, see the audience and, see whether they're picking up and nodding their heads yes, or they've got that big wide-eyed deer in the headlights look. But I hope you're able to follow along with this. I think it makes a lot of sense. Okay, so let's see what's going to happen next. Well, we're still not out of the weeds yet in terms of this design and the complications that are involved, because now we've talked about dealing with the hard to change oven temperature and time factors by grouping using the split plot approach. So we've got that figured out. But then the other problem is the way these models are set up. We end up with too many terms if we're not careful. And this is where Kowalski, Cornell, and Vining came into play, and they developed this tool, this design that's kind of a hybrid design that only crosses the main component effects with the main factor effects. And that way we preserve the advantage of doing a combined design, but we don't put in all the higher order terms that sometimes can accumulate to 6th order or higher type terms. So without getting into the details, and I'll give you a reference later to study, what it amounts to is if you do a brute force mathematical multiplication of the models, let's say quadratic by quadratic, even with just 2 components and 2 process factors, you end up with 18 terms, which means you have to have 18 unique combinations. So already the KCV model gives you almost a 50% reduction while retaining the ability to see that mixture process interaction, whether there's synergism or antagonism. And of course, as we add more and more mixture components and more process factors, the cross model, continues to increase exponentially. But you can see that the KCV model, doesn't really increase that much as you move forward here. And so it begins to get really, really helpful to eliminate a lot of superfluous combinations of things that are just used to estimate very high order terms in the model. So this, was put together into one big experiment, and we added one more thing because the design still was fairly large, which was to block it into 2 groups. And this really put, me and Greg and actually the software to the task. So it took us a while to build these designs, and it was kind of a challenge, for all of us, the people trying to set this up, Greg and myself, and the computer to put together an optimal design. But with a lot of patience and just, dealing with long builds, we finally succeeded. And of course, we've got to give a lot of credit to Greg's student, Jessica, who actually did the experiment and also came up with some very clever tests for the attributes of the cookies, such as, in particular, the crispness of the cookies. So what I'm going to do now is I'm going to open up the chocolate chip cookies, and we'll go over the design layout, and see how it's grouped together by day, by group for the oven temperature and time, et cetera, et cetera. So in red is my little cheat sheet. So I'm going to go back and forth and to remind myself of how to demonstrate this. I've got this little list here. So now I'm going over to the program. And so at this point, we've got a lot of small print. So I'm going to actually magnify this a little bit, but this is the actual recipe sheet. And basically, you would take this and you'd print it, and then you'd start collecting the data that's over here in these last columns, 1 through 7, are the responses, and you can see there's a lot of responses. But let me expand this by doing Control mouse wheel and begin to look at the structure of this for the factors. Okay, so you can see first column, I've got block. And so this design was built in a way that was optimally split for the runs to run on Saturday versus the runs on Sunday. And this took us a lot of negotiation with Jessica to figure this out. How many runs is she willing to do? And this is very ambitious, I have to say. Okay, now we see the next column, which is the group. And this is the split plot. So over here then for the temperature and time, you see that in group 1, the temperature set at 325 and the time at 18. So now these whole plots are randomized, but they're grouped. And then within the whole plot are the different recipes for the cookies, for the butter, sugar, which is the granulated sugar, the brown sugar is component C, vanilla in grams, this one had no vanilla, and then she baked the cookie. Now going to the right, we see that she had a taste panel that rated on a 1 to 9 scale, where 9 is at the top. And they looked at the appearance on a 5-point scale. They evaluated the softness of the cookie, and this was personal preference, but in the end is whether they wanted soft or crispy. And then the weight was measured and other physical attribute of the length. And then she had a very clever test for how crisp it was, which was pictured on the original slide, where she would put pennies on the cookie until it broke. And this one was so soft, it must have broken right away. And then she measured density through, I think, a water displacement. See, there was a lot of thought gone into how to do these measurements. And Jessica was very good. Greg had ideas, and I contributed to the brainstorm. So this is the structure of the experiment. Oh, and of course, we shouldn't neglect, what the outcome was. And primarily, then our focus would be the overall taste liking. So one of the things I always like to do is sort. And what I'm looking for is I want a broad range of results, and it's going from 2 at the top all the way up to 8.33. That's good. And in my popcorn experiment that I did with my son Hank when he was in 5th grade, which was also the year that I had him and his 12 compatriots in the Webelos den, I explained to Hank that when we did the popcorn experiment that we didn't want them all to taste good, we didn't want them all to taste bad, but we wanted a range of taste. And in some regards, bad is good. And a 5th grade boy readily takes to that approach, that bad is good. It's probably not a good thing to tell a bunch of 5th graders, but it works well for experimentation. So this was good. So that covers the first part of my little demonstration of this experiment. Now let's take a look at how we can build this, and I'm only going to go to the optimal screen. And by the way, we build these combined designs as D-optimal rather than I-optimal because we're looking at effects, and so the flavor for the optimality is going to be D in this case. So let's go ahead then, and I'm going to rebuild this by reusing the same factors and responses. And we see that straight away, that we're not in the normal factorial build part of Design Expert. I'm actually using Statis 360, which is a superset of Design Expert, and it adds in this Python script editor, but it's primarily comprised of Design Expert. We have response surface methods, which would be a good thing to run if we want to optimize the process settings in the kitchen for the oven. And then we have mixture design, which if we were strictly looking at the components of the recipe from the Martha Stewart, we would be doing that. But no, we want to do a combined design. And so we've got a number of mixture components here, and I forget how many she had, so this didn't quite come back the way I expected. Let's just see if we've got 1, 2, 3, 4. So rebuild it, reuse the same factors. Optimal here, it came back to 4. So I must have reset it by accident as I was clicking through. So there's 4 mixture components. There's 2 process factors, which we call numeric factors. Now, numeric factors could also be amount. So she could have varied the weight of each individual cookie and made small cookies and big cookies. That would be a numeric factor. Categoric factors could be added in. For example, if you had a gas oven and you had an electric oven in a commercial test kitchen, you could split, into those 2 sides of things as a categoric factor. And we can even put, an extra mixture in, and this would be frosting on top of the cookie or on top of the cake. But now it starts to get way too complicated. It's bad enough just having mixture and process for the number of combinations. So here we see that we've got a total for each cookie of 64 grams, so that's fixed. We've got the ranges of the butter, and in the middle of the range would be probably the Martha Stewart recipe. Might have called for halfway between 18 and 33. And for the granulated sugar, the brown sugar, and then the vanilla. And this would be where if we had Jessica handy, she could explain a little bit more of what her thinking was in doing this experiment. But time is not allowing that. So next we go to the numeric factors. You got time and temperature. And notice that this is set as hard to change. Now, if we were going to do it the other way with the Easy Bake Oven, we could switch this to the hard, and then all of the mixture side of things would be considered hard to change. And then this would become easy to change because we have an easy bake oven, and you could put, whatever you mix up for your cookie batch into the oven, and then you can systematically vary the time and temperature, one cookie at a time. However, for most of us, we're probably going to go with this route of mixing up individual cookies by the differing compositions and putting them on one tray, and then grouping that as the hard to change with the time and temperature. We also had some discussion of setting the oven at a temperature and then letting time be easy to change, where you start taking cookies out at various times. But we thought that got too complicated and we weren't quite sure how that would affect, the results. All right, so I'm sure you have questions as we go along here. So, jot them down or type them in to Sherry, and at the end, she'll come back at me with your questions. Okay, so now we get to the optimal combined design screen, and this is where things get kind of fun. Couple of things here is that I'm partial to doing what's called a point exchange rather than allowing both exchanges, which include a coordinate exchange that can float around places. And so I usually advise going to the point exchange because that gives us geometrically registered point to choose from. And in this case, there's 4,321 points that could be selected because of all the combinations. Now, we require 22 model points, which is shown over to the right here. Because of this KCV model selection, we're not trying to estimate all the possible terms that you would get if you did a quadratic by quadratic. So if I switch to quadratic by quadratic, the required model points jump from 22, I think it was, up to 61. And this is the reason we're going KCV, because it's going to be too many model points. And so this would have terms that begin to go third order at this point. And here we have some fourth order terms. And by the way, the small case letters, which are the process factors E and F, represent the hard to change. And the large case letters are the easy to change, and that's the mixture components that we're studying here: the butter, granulated sugar, brown sugar, and vanilla. And those are locked in. So by going to the KCV, we restrict the amount of crossing between the mixture and the process. So here's some different crossings of component A with E and F, component B with E and F, C with E and F, and D with E and F. And then this is within the process factors themselves, the interaction of time and temperature EF, the pure quadratic term E squared F squared. But a lot of the other terms are turned off now, see? So this is a compromise model, but it's effective to reduce the number of model points. Now then we get into some complications with the split plot, because you can take the number of required groups and augment that with additional groups. And we do this to try to develop an experiment that is kind of convenient and sensible for the number of cookies that you have grouped together per oven batch. And I won't get into the details of it, but just to say that it's hard to come up with a practical layout. And you just have to try some different things as you go along. Now, I'm not going to press next at this point because of the build time is so long. So I'm just going to cancel out of this and reopen this file. And not sure what happened with that. Hold on a second. Let me just reopen Statis 360 and just see if I can get this back to the original. Okay, here it is here. Okay, so here again, we have the structure of it broken out into 2 blocks, Saturday, Sunday, the grouping with the different times of temperatures, and then within the group, varying the recipe of the cookies that were put on the tray. So And I think she probably made multiple cookies. You know, for each recipe, she made a number of them. So there was actually some repetition, I think, that was involved here, but I'd have to go back and look at the report. Now, when you pick up on the slides of this, then you can go and find this link, or you can go to our website and look under case studies, and you would find it. So Jessica was kind enough to provide her report that she gave to Greg Hutto, and we posted that to the website. Okay, I think I've pretty much completed the discussion of the design of the experiment. And so then it was a matter of analyzing these, and just to look at one thing, which is the taste. Then we see that this defaults to the design for a model of KCV. You do the analysis of variance using the specialized restricted maximum likelihood approach that deals with this grouping or non-randomization. And so you can see some significance here. And not surprisingly, the subplot, which is totally randomized, tends to give you more significant outcome. The whole plot, because of the restriction and randomization, unless you repeated this entire experiment the following weekend, you're just not going to have a lot of power to see those whole plot terms. But you notice in the subplot, we've got the combinations of the mixture components with the process factors that are included in the more powerful estimates. So this actually works pretty good. Bottom line, just kind of, looking at the fit statistics, adjusted R-squared is good. Diagnostics look good. And then you get into, a lot of graphing to try to figure out what happened. But looking at this, we see that there's, some pretty good tasting results here. At certain combinations of the mixture components. Let's see what vanilla does. Less vanilla, people didn't like it as much. And maybe there was like an optimum vanilla as I'm sliding the vanilla bar here. And when the red points pop up, those are actual compositions that were made. And then time and temperature, if I increase temperature too much, maybe it was burning. As I come down in temperature, it gets better. And maybe the lower temperature level is the best. And how long should we bake them for? I'm sliding the time around. And so we're getting some insights into, what happened here. But obviously, without much further ado, we'd want to use our tool of numeric optimization to find the optimum for individual responses. In this case, I'm just going to look at the taste, but obviously we begin to do multiple response optimization with not only taste, but the appearance, softness, and then, the weight of the cookie, length of the cookie, things like that. So as far as the solution is concerned, just on the taste side of things, here we see that it's kind of hard to pick out, but butter is our first input, and that's showing high butter, granulated sugar towards the low end mixed in with brown sugar, less vanilla, lower temperature, higher time, and so forth and so on. And you might be able to see some type of window here, but it looks like it's fairly broad as we move the vanilla up, temperature up. Okay, temperature starts to have an impact here in reducing our sweet spot. And you can see that the boundaries here, I guess, with some different criteria that I set up here. Taste, well, this is no wonder it was so open. We probably would want to put a much higher taste on this. And I'm just looking through here. I think I'm going to just take these off. This penny test related to, how crisp the cookie was, and then the density. So now I'm just looking at the taste and number one solution, and then, seeing what happens as we move composition. Okay, here's vanilla. Now this is a little bit more interesting because now I have this little window here. If we were to put an X amount of vanilla in, and you could even put in confidence intervals in here to try to do more of a quality by design. Now I did it, so we didn't have enough power to be able to generate those confidence intervals, so that did not work. All right, I better quit while I'm ahead because now I got the computer starting to churn and think about a lot of stuff that I asked too quickly on it. So the recipe that Jessica came up with in conclusion was heavy on butter. She did go to the vanilla free in the end, and then going with the lower temperature for a fixed amount of time, and that gave near perfect on a 1 to 9 scale for the taste. And then she also did a very interesting thing. She considered that, you know, some people like soft cookies and some like crispy cookies. So she actually changed that penny test setting, you know, back and forth to either a low penny test, which is a soft cookie, or a high penny test, which is a crispy cookie, like this one. And she came up with a split in the recipes, depending on what kind of cookie you want. So, you know, all things to all people, you know, let to each his own, have the recipe they like. And so this is the really wonderful aspect of doing the designed experimentation, is that you're able to come up with models in the end, hopefully, that you can then apply using the what if on the numeric optimization. What if you really would like to have a soft cookie? What if you really like to have a hard cookie? And so you can basically set up whatever goals you want, and you can set various levels of importance. If, as I would suggest, the overall taste is the most important thing, then you can give that 5 pluses, and then you can give other attributes such as the crispiness, you know, a little less of the plus level, maybe a 3 plus, and then you know, other attributes like the density, you know, maybe there's some, you know, a liking for having a denser cookie, but overall it's not quite as important. So then we give that a 1 plus rating. So once you have this, you can set up a model. Once you have the model set up, you can do the what if and set up your recipe to whatever you like. Okay, so hopefully I was able to deliver a tasty little presentation here that provided, you know, some whiffums or what's in it for me in terms of illustrating the application of the split plot to deal with the hard to change baking factors, combined with the easy to change mixture components. And remember that we could have flipped this split plot if we had an easy bake oven. What we could have done is made the process factors easy, like they would be by just adjusting the easy bake oven, and make the mixture hard to change and batched those and made one big, you know, bowl full of, you know, one particular type of recipe, and then taken out one cookie at a time, put it into the easy bake oven, and then randomly varied the time and temperature. So it's kind of interesting, you know, how the split plot, you know, fits into the combined mixture process design and makes it really a lot more practical. Then the other thing that makes this practical is for the combined designs using this hybrid Kowalski Cornell Vining model, which minimizes the number of runs, but maintains the ability to detect synergism or antagonism between the component and the factor combinations. And then last but not least, and still very important, is this design incorporated blocking, which conveniently divided the experiment into 2 days. Okay, so let me just ask, and Sherry, I think I might have to prevail upon you again, but if you enjoyed this talk and learned a few things, I hope so. Not trying to bias your response, but would you put that raise hand up? And then Sherry, maybe you could come on mic if you're still out there.
Yep, and I also have a few questions for you that have come in. So,
okay, great, perfect.
Okay.
And so let's hold off for just a second. I've got a couple extra slides here that I shamelessly want to put up, and one of them is the references of the trilogy that Sherry mentioned, the DOE simplified, the RSM simplified. But what we're talking about here, the combined designs, is covered in the one that's bordered in red. which is a formulation simplified. And I want to, give a shout out to Martin, our current president CTO, who joined in, with Pat, who certainly deserves, tremendous amount of credit for starting up Staddies and now retired as well for being my co-authors. And then I've got some other relevant educational resources. And Sherry, maybe just jump in here and tell me, after we give the presentation, will they be able to pick up on these slides and follow these links?
Yes, we will post these slides both on our webinars page, and we will have the links in our Staddies YouTube channel. So we'll post them in both places.
Perfect. And then Sherry, you're going to like this, being our workshop manager, but I just want to, put a plug in for our mixture design for optimal formulations class, which either you can attend as an individual or as a team of 2 or more to our public presentations. You can see that on our website that's listed here, or you can always contact Sherry and her team via workshops@staddies.com. And then we also can provide private presentations, which once you get to 6 or more, it could be fewer than that, but then you have the advantage of choosing your own date and time, and you can even do some customization for your particular industry. Okay, now let's bring on the questions.
Right. Well, the first comment was from Mike. He said, this was definitely not a cookie cutter experiment.
Mm-hmm.
Yeah.
All
Okay.
right, I love puns, so I appreciate that a lot.
Then a couple of people asked about the difference between de-optimality and I-optimality, wondering, why, if you could explain why a de-optimal selection of points is better or more appropriate than the I-optimal for this particular case.
Yeah, and if I want to be totally honest, it really was, of the brains of Pat, Kinley Lawrence, our original PhD advisor, Gary Ohlert, PhD statistical advisor, Martin is currently, our PhD, that, decided that maybe it would be better to go to the D versus the I. It's a very clear decision when you're looking at doing screening and characterization for effect calculation for factorial designs, that the D optimal is more appropriate because of the way that it minimizes the joint confidence interval of all the coefficients in the two-factor interaction model simultaneously, and it tends to put points more at the extremes rather than the middle. The I-optimal is generally used for response surface methods for either optimizing process or mixture, and it minimizes the area under the curve of the fraction of design space, which is better overall for getting a more precise prediction, rather than just looking at trying to screen out or characterize it from effects. And in terms of the mixture process, because of the way that it's a hybrid, it was settled on that the D would be the best. And that's something that I'm probably going to circle back, since this question came up, and kind of question that myself. I don't think it makes a lot of difference in the end in terms of the outcome. So I can't give you an absolutely definitive answer on that, other than what I would say to my 5 kids back in the day when they keep asking me something. I would say just because, and it's just because the experts felt that might be slightly better than the I.
All right, thanks, Mark. Len asked about the block analysis. Knowing now that Staddies 360 can also do a random effect block analysis, was this done with a fixed effect or random effect? And any particular reason why?
That's a good question. Well, it turns out that at some point, and Martin spoke on this when he talked about some of the features in 360, including the ability to deal with random blocks, that probably most of the time the blocking should be handled as random rather than fixed, because lot by lot, which is something I would work on as a General Mills process developer, quite often I would block by lot, and that's a random thing. as opposed to one reactor versus another reactor, which is fixed. However, it seems like the complications of dealing with the analysis of random blocks oftentimes outweighs the practical approach of just simplifying things to a fixed. And so then it's mindful of what Einstein said, is keep things as simple as possible, but not simpler. Where is that line drawn? And so generally speaking, if I think of it, I'll look at, in cases like this, how that would have affected the results. And if I don't really see, that it's changing the outcome, to keep it simple for the clients, I probably would keep it as a fixed block.
Great, thank you. Wolfgang poses this thought. What do you think about the idea of considering the cost of raw materials and energy as factors and achieving the best cookies with the least amount of money and energy? Was this ever tried?
That would be a great idea if we were commercially baking cookies. If Jessica took advantage of this and decided to set up a little operation to bake chocolate chip cookies in her hometown, she would have to start thinking about the cost of things. For the mixture design, it's incredibly easy to incorporate costs because you can set up, using Design Expert or Statis 360, a new column that we call cost, and put an equation in that simply just takes the cost per kilogram or pound or whatever and sets up a little cost equation. The cost of energy for process factors for an oven wouldn't be so hard either. But as you get into other types of process factors, like I would as a chemical process development engineer, it would become more and more tricky trying to calculate what that cost is, but not impossible. So I do think then that you could actually create an overall cost equation that would incorporate not just the mixture part, which is easy, but also the process side of things, which would require a little bit of engineering. And I would put that in as a consideration for sure. Absolutely.
Great. We have one more question that actually I think our next speaker is going to be talking about in more detail, but I'll just throw this out in case you have any comments. When there is a human-based factor like taste, how is this handled? I know an ice cream company that uses a human being to control taste of their multiple flavors.
I know, and so this gets into a whole issue of sensory evaluation. And typically, the simplest thing is to have a trained sensory panel. I wouldn't have just one person, but one person's better than no person. But the first thing is they've got to be very good at discriminating, have good taste buds and have an ability to, be fairly consistent in their ratings. But if you can get a group of people and average them out, then that'll be even better. It'll be more precise, the end result of the average. And of course, at some point you do a large consumer panel. My wife is a preschool teacher, and a good fundraiser for us was to have the folks from General Mills who were working with the sensory group come out to my hometown of Stillwater, set up in the armory, and we had to have at least 120, I think, parents that would show up from the preschool, and then they would set up a specialized type of plan that actually wasn't completely randomized, but that made sure that every given recipe had a chance to be either near the top of the list or near the bottom. And so they kind of rolled it around. And that my particular experience as a sensory panelist with this large group was I do not like Raisin Bran anymore because we were tasting different types of Raisin Bran with different amounts of raisin and bran. And after that, I never wanted to have it again. So there is an issue with sensory, of course, burning out people. They get tired of tasting things. Yeah. So it's quite a science. And we have a number of people, Tom Carr and so forth, that use our software that are experts in sensory.
Great. Well, Mark, I'd like to thank you very much for your talk today. Very fun and interesting and entertaining at the same time.